1-200-6659 or send an SMS to 555. Pan Africa TV, it just gets better.
Scalars and vectors. Now this is a fairly important section that we are starting off with over here, and it's actually, I think, this is where the main body of our physics for the year starts. The stuff we've done previously has been, I think, a lot of revision and basic stuff that we apply to the sciences as we go on through the work. Now, just very, very basically, a scalar quantity is something that only has size. A vector quantity is something that has size, but it also has direction. Now, up until now, we've just worked with quantities. If you work out what is the force, you give the answer in Newton. If you work out how much energy, the answer is in joules. If you work out power, we've never related it to whether it has size or whether it has size and direction. We've actually just worked with quantities that have size up until this point. Now, it's very important to remember that a scalar quantity, the S for scalar, says it's a quantity having only got size, all right? And it's a single answer. So many seconds, for example. A vector quantity has got two parts to it. The one part is the size, for example, 10 Newton, and the next part of that answer telling you something about that quantity is it must have a specific direction. Okay. Now, over here I've got the difference between a scalar and a vector. A scalar quantity has only got size. It's easy to remember, don't confuse them. A vector quantity has got size and direction. Okay? Examples of scalars. Distance is a scalar. Energy doesn't have direction. We use energy, we convert energy. Mass is the amount of matter in a body. It doesn't have a direction. Power is the rate at which energy is converted, but it doesn't matter whether it's up or down or left or right. There is no direction to it. Speed is a scalar quantity, and we'll come back to speed and distance when we carry on. Temperature. Room temperature, 25 degrees today, more or less, doesn't have a direction. It doesn't matter whether it's day or night, temperature still is temperature. It doesn't matter whether you're hanging upside down from a tree or standing with your feet on the ground. It doesn't have a direction. It's just a quantity. Time just carries on. There is not a going forward and backward in time as much as we would like to think about it in that way. And work done is energy used. Energy is not a vector. It's just a scalar quantity. Now the vector quantities, force is a vector. It's got size and direction. Moments. Why is moments a vector quantity? Oh, we've not done moments. I've done it with the grade 11s. Oh, goodness me. Okay. Moments are vector quantities. Now, this is something you've not yet done. We will eventually get to that. Displacement. Now, displacement and distance are connected. Distance has just got quantity, size. Displacement has got a size as well as a direction. Acceleration, we'll be looking at that. You've done weight. Where does weight go? I've been telling you from grade 8. Weight goes Vertically down. If I'm hanging in a tree, where does my weight go? Vertically down. If I'm lying on a roof that's got a gradient, where does my weight go? Vertically down. All right. Weight always goes vertically down. So weight has got a direction. All right. So weight is a vector. Then velocity. Over here we had speed. Now speed and velocity are connected. Speed being the scalar quantity, vector being the velocity being the vector quantity. Now we will get back to them as we get there. And the last one you also don't know about, is momentum, and we will be doing momentum as we carry on through the work. All right. So just take note then. Some quantities only have size, others have size and direction. Now, in science, when we work with vectors, we can add vectors using mathematical rules, and then we would use things like trigonometry. Now, I don't know if you've done trigonometry in math. Not yet. You will probably be starting with it somewhere along the line. Now, in the physics class, we can do it with a mathematical calculation, but we normally do it with a diagram. And when we represent a vector in a diagram, we represent it as a straight line. That would represent the size, and an arrowhead showing you in which direction that straight line is working. When we were busy with scientific processes and the previous chapters, there was a part where we had a look at bearing. Can you remember? And we said the bearing, if the top of the page is 0 degrees, and we work clockwise back to 0, all right? Then we will get 90 degrees, 180 degrees, 270 degrees, and 360 degrees will lie on 0 once again. But we work clockwise, and then I would say to you, if a line works in that direction, we can figure out the bearing of that line by measuring that angle. And the bearing will tell me the direction of the line. Do you follow? Okay, so I will use my protractor and I will measure an angle, and I will use my ruler and I will draw a line of a specific length that must represent the size, and then it's working in a specific direction. That would be a vector quantity, size and direction. I'll give you a scale. I will tell you, for example, let's say it's a force vector that you have to draw. I will tell you a force of 10 Newton, for argument's sake, will have a length of 5 centimeter. All right. That is the scale that I give you. 2 Newton is 1 centimeter. And then yes, when you work on your paper, the top of the page is always north, the bottom of the page is south, the left is west, and the right is east. Okay, as you look at your page. You with me? North, south, west, east. In other words, north, south, west, east. We always, you don't swap them around. Okay. Now, I've said vectors are represented on paper by a line drawn with an arrow. The length of the line is the size, the magnitude, and the arrow will show the direction. So we've got a quantity with size and direction. Unless otherwise stated, north has a bearing of 0, 0, 0 degrees. It's always to the top of the page. So from here, north, south, west, east, we start at 0 degrees and we go clockwise around it. It's easy to remember, okay? The watch goes clockwise. When we add physical quantities, we cannot add scalars and vectors. In algebra, if I have 5 apples and I have 6 pears, 5a plus 6p, what do I have? 5a plus 6b, because I cannot add apples and pears. They're not the same thing. So when we start working with scalar and vector quantities, you must be careful. You cannot add a scalar quantity to a vector quantity, and vice versa. All right? They are different quantities. I can't, for example, if I'm doing a calculation, go and add 10 joules plus 15 Newton plus 36 meters. That doesn't make sense, does it? Okay, because the quantities are not the same. You can only add and subtract quantities that are the same. So, we cannot add scalars and vectors to each other. Only scalars of the same type can be added. This means if I have time, I've got 60 seconds plus 45 seconds plus 36 seconds. They are all in the form of seconds. They are of the same type. I can't go and add 36 seconds to 7 meters. That doesn't make sense. They're not the same kind. So within scalars and vectors, we can also only add like quantities. Only vectors of the same type can be added. And when we start drawing our vector diagrams, if we are working with forces, we can add and subtract the forces. If we work with velocities, we can add and subtract velocities. But I cannot add and subtract a velocity from a force. Okay, it must be of the same type. When vectors are added, the answer is also a vector, and here's a very important term. The answer of a vector calculation, if I add lots of vectors together, the answer is known as the resultant. It's the resulting effect of a lot of vectors. Okay, now the resultant can be in Newton or in meters per second or in whatever vector we are working with. Yes?
Share with us on #LearnOn1. Tell us what you're learning and where you're learning it from. Send us your name and town to the One Africa TV's WhatsApp on 081 200 6659 or send an SMS to 555. One Africa TV. It just gets better.
Going to carry on with vectors. We started vectors a couple of days ago. You've had a test in between. Just very shortly, what is the difference between a vector quantity and a scalar quantity? Yes, and a vector has got size and direction. Okay, we just had a look at the definitions the other day, people. Just very simply, a vector quantity is something that has size, okay, as well as direction. So the answer has two parts. There's a quantity part and a direction part. A scalar quantity is what you have been working with up until now in all your calculations that we have done. You have never ever brought a direction into the calculation. All right. So, scalar quantities: distance, energy, mass, power, speed, temperature, time, work, joules, energy. Doesn't have direction. Quantities that have direction: forces. We've done moments, all right. Oh, we haven't done moments. Oh, the grade 11s have done moments. Displacement, acceleration, weight, you should know. What is weight? Pulling force of the earth on an object, on or near the earth's surface. Where does it go? Which direction? Always vertically down. All right, so weight has got direction. Velocity and momentum, these are quantities that we will have a look at as we go through the work. All right, done. When we draw a vector, we say we represent it as a straight line. Use a ruler. It's got an arrow in because that indicates direction, and you show the direction of that vector by indicating an arrow. Normally, just very generally, when we work with our page, we work with as if the top of the page is north, the bottom is south, the left is west, the right is east. So if I have to draw, let's say, this green vector over here, then I will draw my axis, north, south, west, east, and I will go and measure that angle there, or I can measure that angle there, and then I will go and draw a line. The size of the line represents the size of the vector, and we need to indicate the value of the angle. All right, a vector quantity. So, starting off, the first thing we must have a look at is how do we add vector quantities? Now, in general, if I say to you, a force is acting on this object, and I have a 50 Newton force in that direction, and I have a 25 Newton force in that direction, what would the resulting force be? Yes, 25 Newton to the right. Why? Well, this 25 Newton is going to cancel 25 of those. And what will I be left with? A resulting 25 Newton. It would work towards the right. Can you follow that? If I had that same object, and I had a 50 Newton force, and I had a 25 Newton force acting on the same point, now I will add them together, 75, because they are working in the same direction. All right. In grade 8 and 9, we would ask you questions. For example, there's a table, and on the table is a book. Indicate all the forces acting on the book. What forces are acting on that book? Gravity, downwards. Why doesn't it fall downwards? So, then the table must be exerting an equal but opposite force on the book. Not so? So there are two forces involved on that book. Yeah? But altogether, right? Next. Oh, no, not air pressure, forces. All right? So there are two forces, but they are equal in size, but opposite in direction, so they cancel each other. We will say the resulting force would equal 0. Are you with me? All right. Now, it's fairly easy if the forces work in the same horizontal plane or vertical line. If they are directly in the same direction or directly opposite to each other, because then we just add or subtract them. The problem comes in when they work at an angle to each other. Now here we have one force, a velocity, 30 meters per second. In which direction would that be? West. Yes, remember we said top of the book is north, bottom is south, left is west, right is east. So we can go and say the 30 meters per second in the direction west, or we could have said 90 degrees west of north, or we could have said 270 degrees. Do you follow me? Who's not with me on the 270 degrees? Remember, we said the bearing? That would be 270 degrees. All right. Okay. And then we have another force, another velocity, and this velocity is 20 meters per second in a direction directly south. Now, mathematically, this one is very easy because we have a 90-degree angle. You're all with me? Okay, so how would I solve it using math? We want to find what is the resulting force going to be if I add 30 meters per second and 20 meters per second in the specific directions as given. We would use Pythagoras. All right, so 30 squared is 900 and 20 squared is 400 and 900 plus 400 is 1,300. So this green side is going to be the square root of 1,300. We'll work it out quickly. Oh, it is over here. There. All right, is equal to 36.05 meters per second. Who does not understand that? That's fairly easy. It's just using Pythagoras. Okay? Now, this quantity is going to be a vector quantity. So we've worked out the size of it. Are you with me? What part is missing? Half of the answer. Direction. Now, once again, we can use math to figure out the direction. Now, I don't know if you've done much trigonometry. Have you done any trigonometry? Okay, then this will be Greek to you. But there's a mathematical way then that we can figure out the answer. Like we did mathematically figure out that answer. But in science, we will more often, I want to add a page there. If oh goodness me, where's it gone? I just want to get this vector. Okay, if I had two vectors, 30 meters per second and 20 meters per second working in that direction, let's just go to this one. The first one, we had 30 meters per second, 30 meters per second in that direction, and we had another vector. It was, what was the value? 20 meters per second going down. Okay. We had a vector 20 meters per second working in that direction. Can you see I've got two vectors? I've just gone and pulled them apart. I've not put them on the diagram. Now the question is, I can state it like this. I can say, I have a boat trying to cross a river. The boat travels at 20 meters per second, but there's a current pushing it off course, and the current is 30 meters per second. What would the resulting velocity of that boat be? Okay, now we can put them together in a diagram, and the method that we use, we draw a vector diagram, and there are two methods. The one is a head to tail method, and the other method is a parallelogram method. Now, I'm first going to do the head to tail method. All right. And now you must ask questions if you don't know. Now, when I have a vector and I want to draw a vector diagram, I'm going to draw them head to tail. All right. That is the beginning. That is the end. So we are going to connect them up beginning to end, beginning to end. Okay? Do you follow? All right. Now, if I took this vector, if I took that vector, have I changed its size or direction? No. All right. Now I want to, I'm just going to put it up a little bit higher. All right. And now I'm going to add this 30 meters per second to that one. Have I changed its size or direction? No. Now, the answer is going to be the vector that starts at the beginning of the first one that I've drawn and will end at the tip of the last one. Does it make sense? All right? So my vector, my answer is that. Now, we call this one the resultant. Because I can replace the green one and the blue one as a whole by the red one. You follow? Okay, can you see we've added the vectors head to tail. The answer is the resultant, and the resultant always goes from the beginning of the first to the tip of the last. If I had 5 different vectors that I wanted to add head to tail, I would draw my little axis, there goes my first vector. Draw my axis, there goes my next vector. Draw the axis, there goes the next vector. Draw the axis, there goes the other vector. Draw an axis, there goes the other vector. What is the resultant of those? Straight line going from the beginning of the first to the tip of the last. There it goes. Arrowhead. Remember your direction. Okay, now this one, we still have to figure out the direction. Now, if you have constructed a diagram according to a fixed scale, for example, we would say to you, use 10 meters per second equal to 5 centimeter. Then 20 meters per second would be 10 centimeters long, that line. And 30 meters per second would be 15 centimeters long. Are you with me? So you can go and measure the length of this line with your ruler, and you go and convert it with a scale. Okay? The direction, you will need your protractor. Okay, and you will put your protractor down and you will measure the direction. And you can either state it as a bearing, or you can simply say, in this case, it's going to be so many degrees south of west. Are you all with me? Now, I want to go back to the book. Here they have, where are we now? Oh, goodness me. All right. I said we will leave this for a moment. I'll first go and speak to Mrs. Lowe and see exactly what you do, because I will go and speak to her about that one. Here we have another example. We've got 2 forces. If this is a pole, for example, there's one force pulling the pole with a force of 120 Newton in that direction. Okay. All right. Let's say there are 2 forces. There's a 120 Newton force pulling the pole in that direction, and we have a 50 Newton force acting on the object in that direction. Can you see that this object is going to experience a resultant force somewhere in that direction? But we don't know exactly. So how would we figure it out exactly? Well, we will add these forces head to tail. And where would my answer be? Let's take that one. From the beginning of the first to the tip of the last. Who does not understand that? Okay. Now, these were easy because they were at right angles. But the process doesn't change if they are not at right angles. So here we have an example. I want to keep that one there on the board. Here we have an example. We have 2 vectors. They say Runel and Aini are pulling 2 ropes that are tied to Wilfred. The angle between the 2 ropes is 120 degrees. In other words, people, the angle, that angle there, is 120 degrees. All right? Do you agree with me? We would expect the resultant to go somewhere in this direction. Okay, more or less, if you just look at the diagram. So, now we must go and connect these 2 vectors. There's the blue one, and here's the orange one. They say, okay, Runel pulls with a force of 150 Newton on a bearing of 330. So that one is 150 Newton. The bearing, that angle there, would be, this angle there would be 330 degrees. Do you follow me? Okay? Aini applies a force of 120 Newton on a bearing. There we have the angle of 90 degrees. Use a scale of 1 centimeter being 20 Newton and try and find the resultant of the force. I want you quickly to just take a piece of paper. You don't have to work very accurately at this point. Just, I want you to see if you can just get started on it. All right? You can just work with pencil. Now, we are going to connect them head to tail. They tell us we have a scale of 1 centimeter is 20 Newton. So, if there is a force of 150 Newton, 150 Newton would represent a line how long? It'll be 150 divided by 20 times 1. So it's going to be 7.5 centimeters. So this one here is going to be 7.5 centimeters. All right, and the other one we have is 120 Newton. 120 Newton divided by 20 times 1 is going to be 6 centimeters long. All right, so we need two lines, one 7.5 centimeters and the other one 6 centimeters. Okay, this one is your 6 centimeter line, and this one is the 7.5 centimeter line. So you always start, when you do these constructions, you always start with an axis. Just a tiny one. Construct your little axis. You'll have to sort of prepare a little bit. I would put it slightly to the left. Now, we have to draw the first vector. Does it matter with which one I start? No, it doesn't. And I'll do both. I'll show you. Okay? Let's start with the horizontal one. It's just easier to orientate that one. All right? So you need to measure an angle of 90 degrees. And you need to take a line. Oh, come on. There we go. A line 6 centimeters long and draw it. Yes, you must have an arrowhead because that indicates direction together with the angle measured. Now, the second step, well, you need to indicate the direction, so we need a little axis perfectly drawn on the tip of that one. And now we need to measure an angle of 330 degrees. So we measure an angle of 330, and there it goes. Remember, this angle there is going to be 330 degrees. All right, where's the answer going to be? It'll be the straight line from the beginning of the first one, and it will go to the tip of the last one. So, there it goes. That one would be the resultant. We need to measure the angle as well. So what value do you get for the resultant, more or less? Who got what? The length of the line. The one is 7.5 and the other one is 6. The red one is 6. Who did it fairly accurately? I know I said to you 6.8. 6.8 is that centimeters. Okay, so now we must go and convert it. If we have 6.8 centimeters, what force will we have? 6.8 divided by 1 times 20. So it's 13.6. Is that right? Newton. Who got this, more or less, plus or minus 2 millimeters? Okay, good. It's 136 without the comma. Right. What else must we add here? To vector the direction. So what's the second part of the answer? You need to measure that angle. What do you get, more or less? Okay. Is it 35 degrees? Okay, just 35 degrees. So the direction is 35 degrees. So there is the answer of that vector. Yes? I've got the direction there. So there's no arrow on the direction, you understand? All right. Now that was if we started with the 6 centimeter line. If I started my diagram the other way around, let's say I started with my red one there. Okay, so I will draw my axis. Let me draw the axis there. And I will take the red line. There it goes. I've not changed its direction. Okay. So 330 degrees, 330 minus 270, it's 60 degrees, that angle. Are you with me? All right. My next step, I need my axis there on the tip, and I must take the other vector. All right, we need to measure the angle there, 90 degrees. Are you with me? Okay. Where is the resultant? It must start at the beginning of the first, and it must end at the tip of the last. It's exactly the same answer. If I go and measure the angle, it hasn't changed. Do you follow? Okay. So it doesn't matter with which one you start. The order in which you add them doesn't matter, except at the end when you have to get the resultant always starts at the beginning of the first vector and it ends at the tip of the last. Well, you will say the answer is going to be the resultant is equal to 136 Newton in the direction 35 degrees. Okay. The answer just has two parts. Doesn't matter which one you put first.
Namibia is known for its beautiful wide open landscapes. However, these deserted spaces also pose numerous educational challenges in our country's rural areas. Because of this, many learners are denied access to proper teaching and learning. At EduVision, we believe that education is the starting point to a journey of endless possibilities.
Very soon, we are going to see e-learning. Soon and very soon, we are going.
The plan for EduVision was to identify areas in Namibia that do not have the proper learning resources, a working school or an education center.
Hallelujah, hallelujah, we are going to see e-learning. No more dieting. No more dieting.
My name is Philip Smith. I'm the principal of Educate Academy in Otjiwarongo. The project EduVision, the e-learning program, started in 2017. With a project like this, obviously telecommunication, internet connection is a major thing that needs to be sorted out, a logistical challenge. And the fact that we chose Chunkwe Secondary School as the first school didn't make it easier for ourselves. It's very far from Otjiwarongo, it's far from Buntuk. So the internet connection was a big challenge first of all. So with the help of the telecommunications expert Paratus, they made this dream come true with internet connections via Buntuk, Otjiwarongo to Chunkwe and then back, the whole process. Like I said, it's interactive whiteboard, so the internet speed, capacity of the connectivity and so forth plays a major role. And so Paratus made this dream come true, and they were on board from the first moment. So very grateful for Paratus.
We go
project offers teaching assistance of a high standard in science to rural secondary schools within the learner's own community by means of e-learning. This entails the following: live transmissions of lessons from an equipped teacher in a different location to the students in rural areas, students using their own cell phone, tablet or computer to recall each lesson, and interactive lessons, as well as the use of a smartboard as a teaching aid.
So if we look ahead at the next 3 years, we get information from the Ministry of Education. The future is very bright. So I think there's a lot of schools who can benefit from this program. Like I mentioned before, finances obviously plays a major role in a project like this. So we're very thankful for all the sponsors that are on board and still on board after almost 3 years of the project. So as long as people from the private sector can get involved, I think we can reach many schools in Namibia, because this project made a good start now. We're already seeing some positive results, and we can just call on all the private sector corporate sponsors to come on board and join in this very, very positive project.
It is EduVision's goal to prepare and guide learners in order to make the modern world they are living in accessible to all.
My name is Magdalena Neoma. I'm 18 years old and I'm doing my first year at UNAM Command campus, and I completed my grade 12 at Tsumpe Senior Secondary School. I'm doing education, so I'm gonna teach at Tsumpe Secondary School, because there I really need to go there and motivate the learners. EduVision helped me a lot. It assisted us in teaching for mathematics, physical science, and biology. And it also, we get to exchange learning from other schools like Educate, whereby they teach us, and that's the most thing that we benefited from. Studying without EduVision was so challenging. And when EduVision was introduced at our school, things become more easier. The time where EduVision was not introduced, we were so slow in learning. And when EduVision came introduced at our school, my learning speed increases. Things were kind of boring, and when EduVision came, my mind changed the way I think. I'm really grateful for what EduVision gave us. Our class of 2019 was the first group to make it to perform very well at Tsumpe Senior Secondary School. So it should keep up the spirit. We need that. It should continue to support us.
EduVision aspires to ensure that equal opportunity is offered to every learner in rural areas to tap into his or her own potential while working in an environment which views disadvantages not as obstacles but as unique attributes that can be regarded as powerful assets when given the proper opportunity. At EduVision, we believe that dreams are the foundation of knowledge, and hope always triumphs over experience.
No more problems. Everything is proper. EduVision.
with us on #LearnOn1. Tell us what you're learning and where you're learning it from. Send us your name and town to the One Africa TV's WhatsApp on 081 200 6659 or send an SMS to 555. One Africa TV. It just gets better. We always love to hear from you. Send us your views, comments, and videos with your name and town to the One Africa TV's WhatsApp on 081 200 6659 or send an SMS to 555. One Africa TV. It just gets better.
In a corner of southern Africa lies a vast and sparse land, where endless horizons, dramatic scenery, and untouched wilderness abound. (1,500 kilometers of harsh desert coastline, a mosaic of biodiversity, sub-Saharan savanna, acacia bushland, encased by 2 deserts. Home to wildlife and wilderness abundant, yet ever at risk. This is Namibia, home to some of the most noteworthy conservation success stories across the globe. Initiatives forged, manned, and driven by passionate individuals and groups.
People are busy there walking for more than 45 kilometers a day.
Special species and wild locations under constant threat from an increasingly destructive developing world.
One of the world's true survivors.
This is the story of the Namibian wilderness, the stories of the enigmatic wildlife and natural wonders of her realm.
They are not a threat to anyone, if you understand them.
This is the story of those determined to preserve it, and thereby themselves.
Don't think I want to tell my children one day that we had rhinos in Namibia. I want to show them live rhinos.
This is the story of the last defenders.
We have been tracking them for about 7 days, and on the 7th day, we come across the butchers, and there was a shooting. We are not armed. We having a camera and GPS. We are just hiding behind the bushes. If I don't protect this species, who's gonna do that? So it's that why I sacrificed my life to go on conserve the rhinos.
Armed out in the field with basically a notebook against poachers that are armed with highly dangerous weapons and more. How is this an equal fight?
I started right on the ground as a tracker, and I worked all the way up to be the CEO now, and I know how hard it is. It's commitment and dedication and the patience that you have for the animal. It's really hard. It's like you had something in your house that you are protecting for so long, and when you go away from home, somebody comes and kills it.
You unravel me with a melody. You surround me with a song of deliverance from my enemies, till all my fears have gone. I'm no longer a slave to fear. I am a child of God. I'm no longer a slave to fear. I am a child of God.
Shivalelo shamemeo ahololange oleo ya hololange undavalululilwa homo family onde yo ye
second.
I am a child of God.
I'm kinda under Wakanda, I kind of the hunger for freedom deliberate. I used to carry the memories of sin on my back, size of a pyramid. I guess the message is clear, to live is for Christ is how I deliver it. I am no longer a slave to sin, I'm free, look at the documents. I got an acre in Jesus, my hero, look at the monuments. I am a part of the family tree, yeah, one of the occupants. He paid the price of sin in full, covered emoluments. Sometimes a fairy tale, very well, but I know him very well. He is simple to get, but deep, like 100 buried wells. He's got a name known to man, his name is Emmanuel. I am no longer a slave to fear, I got the manual. I am no longer a slave to sin, why? He's got the manual.
We've been liberated from a bondage. We're the sons and the daughters. Let us sing our freedom.
You split the sea so I could walk right through it. My fears were drowned in perfect love. You rescued me and I could stand and sing. I am the child of God. You split the sea so I could walk right through it. You drowned my fears in perfect love. You rescued me so I can stand and say, I am a child of God. I am a child of God. Yes, I am. I am a child of God.
Through all the pain and all the struggles, you gotta really love you. You never left my side, I wanna embrace you, I wanna hug you. The devil is a liar, his tongue is so deceitful. I used to have a lot of fear, dear God, you the greatest. I know, God knows I'm a child of his. I've got nothing to fear, thanks for the blessings, Lord. In the name of the Father, the Son, and the Holy Spirit, I'm no longer a slave to fear.
I am a child of God, full of faith. I am a child of God. I am a child of God. I'm no longer a slave to fear. I am a child of God. I'm no longer a slave to fear. I am a child of God.
On the Gold Coast of West Africa lies the peaceful and diverse nation of Ghana. I'm pretty close right now to the geographical center of the earth. It is also one of the last pockets for elephants in the wilds of West Africa.
Every country in the world just about has cattle, sheep, goats, horses, donkeys, but it's only Africa that has the real megafauna, the charismatic stuff which people in the rest of the world want to see.
The passion that the staff have for the job.
There's value to a bird which brings birders to a place like this. I mean, this is a birding paradise. we see an intrinsic appreciation and joy from seeing the wildlife out here, but not everybody does.
You can't get to Moli and then will not be passionate about what we do, because you'll be the only one left. Everybody is passionate.
The only worthwhile war, the war against destruction, the war against loss, the war for peace, for balance, for inclusion.
Just out of my way, buffaloes, elephants, tigers, atabi are still in existence.
If Mole fails, then Ghana is without wildlife.
Join me as we journey to the untamed wilderness of northern Ghana to meet these last defenders.
The people within the law enforcement agencies don't really know you're talking about a roan antelope. Somebody thinks it's just like a goat.
Damatimbo yanje tumbo nopo katike kutoa napo. Damatimbo yanje tumbo kienda sonjalo hape njokoloto nopo tushika meke kwa ifo shimo shazinare atulu mbiskiti neshizo momadare ya mamile ina mpimbwa nje yankesha emela nula isambo no matimbo koko wacharambo ndatimbo mukambili ngongo siyo tangonda mona exita mo studio tafikira mochita nani chapombota kombo muzika ndati chapumba tuchiningiro chita ngasi kuyo tangonga epamona mushe pendo ndeiruga exita na mushe ino limo computer kokumana kushe mumti wanjo munike kusheshe. We took it all away with the help of a lot of friends, lot of fans. We took it all away with a lot of brothers, a lot of sisters. Yes, I know we took it all away with a lot of mics, a lot of studio sessions. Took it all away with a lot of shows and misunderstanding, yeah. What's it gonna do what to share? Chika meke paipo chimo chazinare Narobia chipanga no matigo kona kayare Damatimbo yanje tumbo nopo katike kuto wanapo. Damatimbo yanje tumbo kienda sonjalo hape jokoloto nopo tushika meke paipo chimo chazinare atulu mbiskiti neshizo momadare ya mwamime ina mpimbwa nje yankesha emela nula isambo no matimbo koko njarambo ndatimbo mukabili muningo histori na tereka sofaya mepenya simvuko tulimo nawa sotakarika tuningirima yetu mebra minding our business maitunga kwetulandera kwani mu makumba hagetulangeka mukangalo takatifu chasina tukiva mebra demanding our business. Now we start to turn up the tune for the fans. Daddy don't stop. Say now we shall not go mask up. Inspiration, the generation. Every we shall give us some more. Oh, why you sound so low? Every we shall give us some more. Oh, we want some more. How about you chita make a pie for Shimo Shazinare? Narobia chipanga no matigo kona kayare. Damatimbo yanje tumbo nopo katike kuto wanapo. Damatimbo yanje tumbo kienda sonjalo hape njongoloto nopo kushika meke kwa ifo shimo shazinare atulu mbiskiti neshizo momadare ya mwamile ina.
When the live game's about to start, but you're stuck here, we've got an app